In this example, we want to consider two cars that are beginning at the same position. One will be going with a constant speed, and the other one will have a constant acceleration, though starting at rest. Let's say this red car is going to be the one with constant acceleration, and the blue car will be the one with constant speed, and since in the same direction, also constant velocity. So we'll have them start at the same position, and we want to figure out when and where they're going to meet up again as they move along. So first thing we'd like to do is set up some sort of kinematic equation that can describe their motions. In the case of the car with constant acceleration, we can describe the motion of that car, its position as a function of time, with just this equation. So this is similar to the kinematic equation that you've seen, but there's usually also a velocity term, but since the initial velocity is 0, I'm just ignoring that. Adding 0 doesn't really change the equation much. On the other hand, the other car here, the blue one, its position can also be described with an equation, and this one will just be what its speed is times time. So in both these cases, we'll call the initial position 0 just to make things nice and simple. And with that sort of setup, we can see then that at time equals 0, if both times are 0, they'll both have the same position. And eventually, these two cars should meet again. So the question is, where and how might we figure that out? In fact, should we expect them to meet again? So let's actually try graphing these two functions. If we were to consider just the blue car, the one with constant speed in this case, well, we see then that basically for every second of time that goes by, there's going to be a set amount that the position is going to increase. We can see basically that x is a function of t, and it's going to be linear. So it should just be some sort of straight line going through. On the other hand, the red car, the one undergoing constant acceleration, depends on time not as t but as t squared. So this is a more complicated relationship, but a function like this should be looking like a parabola. So if we give it a parabola shape, with this sort of setup we can see there are 2 points where we would meet up, right at the origin and some other point in the future here. So whatever that position is, let's just call it x of m, the position of where they meet. Actually, with this graph, here is position where they meet, and this would represent instead the time that they will meet. So there'll be some certain time, and there'll be some certain position where the two are meeting again, which means that if we were to look at each function, at time tm for this first equation, it'd be at position xm, and also in this equation here, if we plug in tm, then we should also get xm. So what it means to meet is being at the same place at the same time. So how might that look if we write down these equations and work this out algebraically? So what we're saying is that there is some time that the two will meet, and when that happens, the first equation will equal the second equation. So if we set those two equations set to each other, then we could use that and solve for when that might happen, and then we could also solve for where that might happen. So let's set the two equations equal to each other. And so we're going to basically have 1/2 ATM squared equal to VTM, so that time when they meet. And then we can try solving for when that time is. So a little bit of solving. We see that there's a common t on both sides. We can cross that out. And that will correspond actually to the time equals 0 point, so we're not losing any interesting information. We solve then for tm, and that's going to give us the initial velocity divided by 1/2 a, or meaning 2 times v over a. Now, since we said that the initial velocity was 25 meters per second and the acceleration was 1.2 meters per second squared, everything nicely in SI units, we can just plug everything in there and we will get, we're going to get about 42 seconds. And using 42 rather than more decimals just because it's significant digits. Okay, so that's a fair bit of time between the two, but that is a relatively small acceleration. Notice that if we had a larger a, then the time would have been smaller, which makes sense. If the velocity of the first car were larger, then it would take an even longer time for the two to meet. That can also make sense. Notice, though, that the work we've done, we've only found the time when they have the same position. This does not tell us, for example, when they have the same velocity. When they meet, they'll have the same position, but they don't necessarily have the same velocity. In fact, you probably expect one of the cars to be going faster than the other because one of them is playing catch-up. If they were both going at the same speed, they never would have actually caught up to each other. So that's just a little bit of thinking about that conceptually. Now that we have the time, what could we do to figure out the position? Well, that time we could plug into either of our equations up there. So just for simplicity, let me choose the x equation for the constant velocity one. So we can plug in our value that we found there and find out what we can do. In fact, if we want, we could do this a little bit more algebraically and cut down our error. And let's actually just take the expression here and just leave it algebraically and plug it in for Tm. So if we do that, we're going to find then that this equation is going to equal 2 times v squared divided by a. And doing so, we're going to find that that position is, again, to 2 sig figs, about 4,200 meters. Or that's about 4.2 kilometers, a little bit more than 2.5 miles. So it's going to be pretty far away from the starting line when these two cars finally meet. But as you might expect then, the accelerating car is going to be the one that ultimately outruns the one that's going at constant speed, since the one with constant acceleration will be continuing to go faster and faster and faster indefinitely.